بسم الله الرحمن الرحيم أعوذ بالله من الشيطان الرجيم.
وعلم آدم الأسماء كلها ثم عرضهم على الملائكة فقال أنبئوني بأسماء هؤلاء إن كنتم صادقين. قالوا سبحانك لا علم لنا إلا ما علمتنا إنك أنت العليم الحكيم.
So we see that Adam alayhi salam was taught the names of things, and the angels were made to prostrate, sajda, because of the superiority of knowledge. Allah Ta'ala says that can those who know, those who don't know be equal of those who do know? So knowledge is a very precious gift of Allah, and we should ask Allah to give us the useful knowledge and protect us from useless knowledge. So last lecture we studied the how to find the p-values in a certain way in contingency tables. Today I will teach the standard way. What I was saying was that those techniques that I taught in last lecture are not known at all. Today I will teach the traditional technique, the one which is known to everyone and used by everyone. So basically here is one example that we have men and women. This is a survey data of 2,237 women, and the idea is to study if right-handedness and left-handedness is different by gender, or is it the same. So we find the survey, it has 934 right-handed men and 113 left-handed men and 20 ambidextrous, equally able to use both hands, right and left. And in women the proportion is slightly different, the more right-handed, less left-handed. But is this difference significant, or is it due to chance? This is the question. So the null hypothesis formulated that people become right-handed or left-handed according to the chance. So 50% chance or whatever, we will see soon. So the thing is that what you do is, instead of calculating the probability of this outcome, you calculate one statistic, which is the distance of this outcome from the central outcome, the most likely outcome under the null hypothesis. And so we'll show how to do that. So each cell gets an expected value, the number that would have been seen if there was a perfectly equal distribution. So basically, there's a total of 2,004 right-handed men. So you would see them distributed between men and women in accordance to the proportion of men and women in the survey. So if they were equal, then you would see equal, but in this survey there were 1,067 men and 1,170 women. So the distribution of right-handed people between men and women would be in this proportion, 1,067 to 1,170. If the null hypothesis is true, that there is no difference between men and women. So that would be the expected value under the null. So you look at the actual number, subtract the expected number under the null, square the quantity, that gives you sign invariant, and then you divide by the number, the expected number, and that's put in each cell. Then you add up all the cells, and that's your ChiSquare statistic. This is called the Pearson ChiSquare statistic, and this statistic has an asymptotic distribution of chi-squared with degrees of freedom being n minus 1 times m minus 1, where n is the number of rows and m is the number of columns. So here the degrees of freedom would be 3 times 2 is the, so it's going to be 2 times 1, so it's just 2. And why? Basically, because across the columns things are supposed, basically we are thinking of fixed margins. So across the columns things sum to a fixed number. So the sum of the two quantities should be fixed. So that means that only there's one degree of freedom. Once you choose one number, the other one is fixed. And similarly, down the rows, all of the sums are fixed. So once you have two numbers determined, then everything else is determined. So that's the degrees of freedom, because once you have two, you just pick the first two entries, then for the men, the second two entries for the women is determined, the bottom entry is determined because the total is known, and then of course the missing entry is determined. So basically that's the degrees of freedom. And so now I would like to show how this works in a and basically everything that we did last time. Okay, so instead of doing that data, I'm going to do this one. This is the same data we saw last time with the low, middle and high income, and worse, same and better. And so now I'm going to do the ChiSquare test on this. So first thing we need to do is to determine the proportions. So we got to find the expected values. So let's look at the expected value. ये नज़र आ रहा है या इसको मैक्सिमाइज कर दूँ? ठीक है. Let me make it a little bit bigger. Alright, so how will we calculate the expected number of entries in this cell, W and L? It's going to be 58 over 189 times 47 over 189. These are the two proportions, and then times 189. So one of the 189s will disappear, and we can take it as 58 times 47 divided by 189. So let me write that. Equals, should I do it by cell reference? No, let me just do it simply. 58 times 47 divided by 189. So that's 14.4. Now let me see. There's a way to do this. Let me try to do it cleverly now. There's a way to do this so that it will remain the same as I go down. Yeah. So as I go down this, I want to keep the. So I will write this as $B and 5. As I go down, the 5 will keep changing. I don't want the 5 to keep changing. B will remain the same. $5. Yes, $5. Now, as this goes down, the 5 will remain fixed, but and the B will not change. Okay, let's see. Let's hope. 47. नहीं B अभी देखो. $5 star.
E2.
Yes.
E2.
$E2, I think. $E2
Sorry.
slash 189.
E2 को फिक्स करके सर हम
देखो पता नहीं क्या होता है. Let's try to see if it works. There's a way to do this so that it works, but let's see if it works. Alright, now this is $5 times E3, exactly, this is working, right? And this is $5 and E4. So this is now correct. Now, if I catch this and move this over here, now this is $5 times E2. So you see this works, right? This is how you make a table if you don't make the table. This is how I did the last lecture's big table. If you put dollar in the right place, then you get the whole table without any. Okay, so these are the expected numbers. Now we want to calculate the chi-square statistic. So I'm just going to calculate equals this. I want to put a parentheses. B2 minus slash
उसका स्क्वायर
क्या हुआ? ओ हाँ, इसको स्क्वायर चाहिए. Square divided by. So are you guys familiar with the chi-square test? Little bit. Okay, so this is 2.152. So these are all the 9 numbers, right, that we need, and I want to sum all of these. I think I can sum the whole thing. I2 colon K4. Yeah. So that's 5.2. Now I want to check this against the critical values of the chi-squared. Huh? क्या हुआ?
Against conventional table, it is significant.
significant.
Oh, it will be significant. Why?
chi-square हम 0.4 से हम
Okay, here's chi-squared.
3.84 होगी इसकी 1 पे.
अच्छा, chi-square dot test. Now I don't know these things, so I have to look at what this is going to do. ये अच्छा गलत हो गया. Okay, now what I want to do is to look at the help for this to see what it tells me. Actual range, expected range. What? This is actually going to do the test on the whole thing? Very interesting.
I think it will going to calculate that chi-square value.
Yeah. It is going to calculate. So I don't need to do all of that. Okay, let's try to do it like that. क्या हुआ?
Chi-inverse.
I-inverse? No, chi-square test. This is you see, this is going to, you can just feed it the matrix. Right, like this. Actual range. And then the expected range. Although it should be able to compute the expected range by itself. I don't know why it wants us to do that. .266. So this is 26% p-value, which is not significant, but let's do it a little bit more slowly to see if this is correct. Equals sum. See, what I'm surprised at is why is Excel asking us to calculate the expected values when it can do it so itself. So 5.2 is the chi-square, and now let's see what the chi-square distribution does. Chi-square dot inverse should be the one.
Chi-INV.
Huh? Chi-squared, chi-SQ. Chi dist, huh? And chi inverse. Okay, let's look at chi dist. Chi dist of x, okay, 5.2, and degrees of freedom is 2, right? 2 nahi, 4. This is 4. 3 by 3 table, so 2 by 2 is the because of the fixed margins. If we didn't fix the margin, it could be 9. And yeah, to hoga obviously 26%, which is exactly the same thing that we got last time. So this is not significant. So basically, the same conclusion as we got last time, that this is not significantly different from the null hypothesis. That so we don't have any evidence that the null hypothesis is wrong. Now, there are two things here that I want to note before we go ahead to the next topic. One of them is that when you calculate the chi-square, now you have a continuous distribution. So in general, our methodology is that we want to calculate the probability of the observed outcome and then calculate the rejection region, which is all the points which have less probability, and then calculate the p-value, which is the probability of the rejection region. But there's a problem now with continuous variables, that there is no probability. The probability that the chi-square equals any particular value is always 0. That's because in continuous variables you have densities, you don't have probabilities. You have the probability doesn't occur at any one point, it occurs in a neighborhood of point. So there are two ways to fix this problem. You can take a small neighborhood of that point. So if here the value is 5.21041, this is the value of the chi-square statistic. The probability that chi-square equals 5.21 is 0. But you can take a small interval. You can take this value plus or minus epsilon. So if you do that, then you can calculate the probability. I'm thinking of the simulation method. So you can calculate the probability just by calculating how many times you fall into that interval, and then you can calculate basically what you need is the density. The density can be, now to calculate the density, of course we know by Pearson's calculation that this density is asymptotically chi-square, and we have the formula for the chi-square density, so we can actually calculate the value of the density at this point. If we don't have the analytical formula, and sometimes we don't, in fact there are many statistics for which the density cannot be calculated analytically. So in that case we can use the simulation method to calculate the approximate value of the density. If you have the probability in interval of plus or minus epsilon, then the probability is equal to 2 epsilon times the density, because of the rectangular approximation, because the density is approximately equal to the value of the density is integrated to get the probabilities. So that's one way to get that probability, and then you can work it like this. But the problem, the point of using a distance measure, this measure, the chi-square test, is measuring a distance from the null hypothesis in some sense. So in this case, the rejection region becomes very easy, because there is only one way to go. If the distance becomes larger, the probability becomes smaller under the null. That's the usual case. There are some strange cases where this doesn't happen, but 99% of the time, and you can rely on this. So then we don't have any difficulty. We don't need to calculate the probability, because all values of t bigger than this, all values of chi bigger than this are lower probability. All values closer to 0 than this are higher probability. So the rejection region is easy directly. You don't need to calculate the probability, and So basically what we do is, to calculate the p-value, I need to know the probability that the chi-squared is bigger than 5.2. That's all. So if I calculate, and this hopefully 26% is that probability, it could be 1 minus that probability. In either case, it doesn't matter. This p-value is not significant. It means that the null hypothesis is supported by this data. Now, in traditional books, everywhere you will see that what is written is that null hypothesis can never be proven, and so you can either reject or you can fail to reject. But this is not actually true. What they are saying, basically, you see in our formulation, this is not true. In the way the standard setup is, they say that the null hypothesis true means that the data is actually truly distributed according to the null hypothesis. And if that's true, that's something you can never find out, because it has so many implications, you cannot test all of them. So this is just one test, and failure to matching on this ground doesn't mean that you have proven the null hypothesis, because the null hypothesis is very strong. It says that the data itself is randomly distributed according to the null hypothesis. How do you know? I mean, this is just one test. There could be 1,000 other tests, and if any one of them fails, then the null hypothesis is false. So basically, but what I am saying is that what we are testing is for a match between the distribution and the table on this ground of deviation from the null. So when we accept, we have a match on this ground. That's all. No complications. So this is a different way of thinking about the problem. And so here we say that, okay, in terms of proportions, the table's proportions match those that are produced by the null hypothesis. Yes, true. So we accept the null hypothesis. We don't fail to reject the null hypothesis, because our null hypothesis is different. Our null hypothesis, there is a match. It's not that they are exactly the same. This is the difference, this is the confusion which is occurring throughout in the classical probability, is that they are taking the model for the reality and they are mixing it up with the reality itself. And that's why you cannot test the null hypothesis. If you keep the model and the reality separate, then there's no complication and no difficulty. Okay, so those are the issues with the null hypothesis. Now, the contingency table. Now what I want to do next is, so that's the last, basically, issue in the contingency table. Now we want to go back to the beta binomial estimation and show how this relates to that. This relates very closely, even though it may not seem that way. Now we are going to look at some real data, which has been provided to be by Zahid Asghar yesterday. Okay, so there's the cricket data for, is this, should I magnify this? Okay. So these are the number of matches. This is Afghanistan. It played 17 matches, test matches, summary one-day matches, 2015. 17 one-day matches were played by Afghanistan. It won 8 and it lost 9. Australia played 18 matches. It won 15 and it lost 3, and there was no result in one. I've actually modified the table a little to take out the no result, because that was going to cause me problems. So in fact, I'm going to delete this column, because original table has 19 here. 19 matches played, 15 won, 3 lost, and 1 no result. So I'm going to take the no result out. And I've subtracted the number of matches. So now there is so total number of matches played were 282. 141 were lost and 141 were won. How come? Why are these two numbers equal? If somebody wins, somebody loses, yes. Right. Now, these proportions are C3 over B3. So this is the proportion of wins. Now I want to test a null hypothesis that may seem very strange. Suppose that every match is just a completely random decision. There is no skill, nothing. It just looks like this is an illusion that we have. So it's an interesting null hypothesis that it's completely random game. Anybody can win. It's equal chances for all. But and this actually is known to happen. If some lottery winner wins the lottery, it's by pure luck. But you ask him why, he said, "Oh, on that day I had my lucky rabbit's foot, or I was wearing my special amulet, and that's why I won." So people create causes for random events. So this is the null hypothesis. So it's interesting. What do you think will be the result before I do the test? I don't know. How many people think that we will see a difference? You see, if there are some teams which are highly skillful, and some teams which are very bad, then there will be strong deviations from the null, and so we will reject the null. But so it's not set clearly at the beginning before we do the test as to what will happen. So any guesses? Who thinks that this will be random? How many people in favor of completely random? No? All right. So most people, Atiq says it's completely random. But most of the class thinks that there will be skill. So okay, we'll see. So now, how do we get the expected values? Let's see. Oh, I can put the table. Oh wow, I can just tell. But it still wants the expected values. I don't know why they want the expected values. Okay. So by the way, how many degrees of freedom will there be? Okay, so what's this going to be? The expected values is going to be just 50% of the number of matches played, because in this time, unlike usual, the probability of winning must be 50% if it is to be random, because wins must equal losses. It can't be that all have some probability P of winning which is different from 50%, because probability of winning for someone is probability of losing for another person. So we just take 0.5 star B3. So 8.5 is the expected number of matches, and that's of course correct. 0.5 star. And these are the... Oops, ये क्या हो गया? No, there are no ties. Yani, I have taken them out. Yani, I didn't see any ties in this table. Okay, so under the null hypothesis, Afghanistan would have won and lost 8.5 matches. And these are the expected. And now, let's see if Excel will give me the answer. Equals chi-square test. Okay, chi-square dot test. Now in the chi-square test, it wants the actual range and the expected range. So we take the wins and losses. This is the range, the actual range, and this is the expected range. So I'm taking this shortcut because I assume everybody knows. Ooh, significant, highly significant. Huh? Kya hua? So it means that the null hypothesis that it's completely random can be rejected. What? Why? What's so funny? Shocking. I was betting on the completely random. See, the fans of cricket would not like if this. Huh? Bookies bhi hote hain. Haan, right. Yeah. Okay, so now let's see. Okay, let's do it a little bit slowly because we'll get some more information that way, and also I will be able to confirm that this is true. So we have equals. Oh, acha, I want to do this parentheses. Okay, so that's the entry for this cell 029, and now I think I can just copy this over, right? Next to the next cell, and then I can copy this down. And then I can just sum. Okay, so now the thing that I wanted to look at here is the numbers which are big. So basically one is Zimbabwe, which has 4.2. कौन सा? Scotland is big. Pakistan is performing 50-50. Yes, 12 and 14. So it's not a problem. And basically anything which is far from 50% is going to be triggering the chi-square that this should not be happening, because 50% is the normal value. So Zimbabwe, which lost 23 matches, is one outlier, and then the second one is Scotland, which lost 8 matches,
West Indies.
and Bangladesh is also an outlier, 1.7, and 1.95 is New Zealand. New Zealand. Scotland. So these are the big numbers. West Indies also 1.6, yes. Okay, so I just want the sum of all of these to get my chi-square. Sum from, okay, so it's K3 to L17. And what's this? 45. So it's a big number. And now I want to test this in chi-square of 16. It's a 70. Oh, no, not 16. How many countries are there? 3 to 17, which means that there are 15 countries, I think. Yeah. So there are 15 countries. So 15 minus 1 is 14. 2 minus 1 is 1. So it's 14 degrees of freedom that we're looking at. So we look at equals chi dist. Okay, now what I want to do is to make sure that this is the right number. Okay, right-tailed probability. So this is the probability of being bigger than or equal to this number. So it's not the standard distribution function. Okay, so we want to put 45.26 and how many degrees?
44.26.
Oh, इससे कोई फर्क नहीं पड़ता. 2, 6, 4, 4, 6. 14. Yes, very, very low value. इतनी value थी पहले?
Yes.
So this is the same thing. So basically, we reject the null hypothesis that this is a random outcome. So it means that there is some skill in the game. I'm so surprised. So maybe Imran Khan does know something. From his behavior, it seems very unlikely.
सर अगर ऑस्ट्रेलिया और जिम्बाब्वे का मैच होता है तो ऑब्वियसली बात है कि उसकी स्किल्स ज़्यादा वो जीत जाएगी ऑस्ट्रेलिया और जीतती भी है.
Yes, anyway.
Maybe
That's what.
another analysis would be nice if we apply this kind of analysis for T20 matches.
Yes, you can do that. There are also, you see, there is a lot of things that you can do with this. Now you can say, you can ask the question, is, I mean, I'm looking at the probability, but you can create a Pij table. You can say that the probability of win for country A versus country B depends on both countries. Here I'm just taking a null hypothesis in which there is one probability of win each country has, which is 50%. Suppose I change that and I say, okay, there is a, for any country, pair of countries ij, there is a probability Pij of winning for country I against j, which would be 1 minus Pij for the country j against I. So with that hypothesis, again, you can test for a match and you can estimate. Now we are coming to the second part. Now testing is done, and now what I want to do is to estimate the probabilities. So what I want to do is now I want to ask the question. So we have this model that every country has a probability of winning, and we want to assess this model. And now we see that the probabilities are going to be different for different countries. So here we have 47% is the probability for Afghanistan of winning its matches. 83% is the Australian probability because they won 15 matches out of 18. And Bangladesh has 72%. And England has 48%. Hong Kong has 100% probability of winning all its matches. It played 2 and it won 2. So India has 59% and Pakistan has only 46%. Ireland is the same as Pakistan. New Zealand has 68%. Okay. So now these are the observed frequencies of winning. Now if we think that, so this is a sequence of ones and zeros we are seeing. 1 is win and 0 is loss. And Afghanistan has a sequence of ones and zeros in which there were 17 totals. So the outcome, W, is a binomial variable with n being equal to 17. And now P, we have rejected the 50%. So what is the P? Well, our best guess for P would be 47%. So now we are, now this is the estimation problem. Now we are coming back to the Bayesian theory. So suppose I want to estimate the P for Afghanistan. Okay, so that's 47%, because basically what we are saying is that the observed frequency, observed proportion of wins, which is 8 over 17, should match to the true probability, which is something, not necessarily 47%. Now actually we have also a confidence interval for this. Okay, so now I'm going to copy this data on some other sheet so that we can do the estimation exercises. Okay. Right. So we have binomial random variables, many of them, and these are the observed outcomes. In the first one, binomial NP, the observation is 8, the second one is 15, 13, and so on. Now, if we use classical statistics, then our estimate of the probability of winning for Afghanistan is 47%. This is the observed frequency of winning, and this is also the maximum likelihood estimate. I think I discussed this theory. And this is the maximum likelihood estimate, And what about, so this is the, so the probability P, this is the binomial function, n choose y, pi to the y, 1 minus pi to the n minus y. This is the probability of y, the observation of y given pi, the probability. Now, in the maximum likelihood method of estimation, the first thing we do is that we switch our orientation and make this the likelihood function. So to make this the likelihood function, this is what it is, what is written here. The likelihood function is the same function, but it is a function of the probability P, which is pi here, and the observation is now fixed. Previously, when you look at it as the density function, then the pi is fixed and the y varies across the outcomes, and for different outcomes it has different probabilities. But now the y is a fixed number, the observation 8 here, and now we think of this as a function of p. So different values of p give different values of probability for what you actually saw, which was 8. N is 17 and you have 8 observations. So you've put the n at 17, you put the y at 8, and so now you have 17 choose 8, pi to the 8, 1 minus pi to the 17 minus 8, which is 9. This is your function of pi. Now you say, okay, what is the value of pi which will maximize this? This is the maximum likelihood method. That what you saw, choose the value of p which will maximize the probability of what you saw. It's a sort of a logic. There is no guarantee to this, but it's a good logic. Yani. So it's easy to maximize. You can, especially it's easy to take, if you maximize, if you take logs. One thing important to note is that maximizing the likelihood will lead to the same result as maximizing the log likelihood. This seems a little bit strange sometimes. Log is a monotonic transform. So it's well, whatever value of pi maximizes the likelihood, the same value also maximizes the log likelihood. So after you take the log likelihood, it becomes y times log pi plus n minus y times log 1 minus pi. And now when you differentiate this with respect to pi, it will be y divided by pi minus n minus y divided by 1 minus pi. And if you do a little bit of manipulation with that first order condition, you will end up with y equals pi hat equals y over n. The maximizing value of pi will be y over n. So the maximum likelihood estimator of pi is just y over n, the observed frequency, which is a reasonable estimator. It says that if you want to know what value of p maximizes, so these are the maximum likelihood estimators. Now this is not enough to have the estimator. What you need is the variance of the estimator, or the SD. So we have that also. Equals, what will it be? Square root of
SQRT.
right. It's going to be P times 1 minus P divided by n. What is n going to be? It's going to be the total number of matches played. So it's 1 to 1. Okay. So these are the variances, the standard deviations, and as you can see, what I've been telling is there's not that much difference. I mean, you're seeing 7% up to 14%. For Ireland, you have 14%, and for Zimbabwe, you have 7%, and things are varying in that range. So now we can form the 95% confidence interval. Lower bound 95% and upper bound 95%. So this is going to be equal to the estimate minus 2 times the standard deviation. Oops.
Should be in numbers. What's the percentage which include the number?
I just want to get this thing. And now okay, now I can okay, and now the upper bound will be the same thing. इसको percentage से change करके number कर दें. Equals this plus 2 star this and okay, so now I have got the upper bound and the lower bound. All right, now in the so this is the thing. This is what the conventional inference tells us. This is now I'm going to conventional inference tells us that the Afghanistan, it has the probability of winning, which is between 22.8% and 71.3%. This is the 95% confidence intervals. Now, one very important thing is that there is a huge controversy and confusion. What does this 95% confidence interval means? This is because what the classical theory says is that there is some true value of P. So now the question is this true value inside this interval or not? So the standard interpretation that people try to put on the 95% confidence interval is that there is a 95% chance that P, the true value, is inside this interval. And there's a 5%. But everybody understands that this is impossible because P, the true value, is a fixed number. 22% is also a fixed number. 71% is also a fixed number. So there is no probability here. P is either inside or outside. So then there is a big mystery and people are always confused about what is going on and what does confidence interval mean, and there's huge number of papers written on this. Now all of this is nonsense because basically the problem arises because there is no match. I mean, because they don't separate the model from the reality. There is a saying that the finger points at the moon, but it is not the moon. So if you mistake the finger with the moon, then you are in trouble. So what I am saying in this approach is that there is no true model. There's only some models which can match and some models which cannot match. The fact that the model matches doesn't mean that it is true. So once we get rid of the idea of a true model, then there is no difficulty with understanding the 95% confidence interval. The 95% confidence interval is the set of values of P which provide a reasonable match to this observation. That's all. So all of these values are providing a good fit at the 95% level. If you go outside this, then the data will be rejected. The data will reject the match at the 5% level. And within this, you cannot reject the match at the 5% level. And that's perfectly, and this is perfectly sensible. So all values of P between 22.8 and 70.3% are matched to this data. That's all. And there's no confusion and no problem. Okay, so now here we see in Australia the first case that we reject the hypothesis of 50%. You see, that's why this is why the null hypothesis is being rejected. Australia is much better. 95% level, you would reject you could probably check, you should check that if you put in the null hypothesis 50% for Australia, what is the likelihood of this event? It will be fairly low. So the p-value. So the bound is 65 to 100.9%. This is 51. Okay, so this is Bangladesh is slightly better than 50% at 95% level. This one, England would not reject the null of 50% because it's inside. Hong Kong. Now there is a problem, you see. This problem arises always in maximum likelihood estimator with the small samples, leads to a very bad estimation because there's lots of variability. Basically, one thing you can prove is that maximum likelihood is a very good estimator in large samples. If the sample size becomes very large, then the maximum likelihood estimator becomes very good. But at the same time, in small samples, it can be very bad. So here is a place where in the small sample it has become very bad because the SD, square root of p minus 1 minus p, became 0. And so, but remember that SD is being estimated by bootstrapping. As I said, bootstrapping works fairly well near the center. For p equals 50%, for even from 10% up to 9%, it works fine. But as p goes close to 0, then the bootstrapping becomes bad because the difference between 0 and okay, so let's say you see what is the actual range here. There were 4 matches that were played, only 2 matches which were played. So there were 3 possibilities, 0, 1 or 2. 50% chance of at the null hypothesis 50, it would be 50% chance of 1, 25% chance of 0 and 25% chance of 2. So if you want to make a 95% confidence interval for what p can be, it will include all 3 values. There is nothing which can reject anything. So 0, 1 and 2, all 3 values are compatible with the null hypothesis of 50% and with many others. So the range of p is very indeterminate. What are the values of p which are compatible with 2? You can determine that actually, and that is actually a good idea. What is
आपने y और n की जो बात की, तो ये वही वो frequentist approach है, उसी को follow करते हुए ये calculations हम करते हैं.
ML maximum likelihood is frequentist. Now if we understand the concept of the confidence interval, then we can create a correct confidence interval for this, because what do we want to know? We want to know what is the value of p which can generate the value 2. So now if p was, for example, 10%, then the probability of 2 wins would be 1% only. So a value of p, winning probability of p of 10% is not compatible with this data at the 5% level. You see, all high values of p are compatible with the observation of 2. I have I have one observation. My observation is that there were 2 wins in 2 matches. So now I'm asking, what is the possible value of P which is compatible with this observation? So if P is 50%, the probability of this observation is 25%. If P is 25%, the probability of this observation is 1/4 times 1/4, 1/16. It's basically P squared. So now I want to make P so small that the value is 5%. So all I need to do is to look at the square root of 0.5. 0.05. Okay, so 22%. So the lower bound for P, according to the correct logic of confidence intervals, which nobody knows, is 22.4%. So now if I want to make, if P is smaller than 22.4%, then the probability of seeing the outcome 2 is less than 5%. So we could reject the null hypothesis at the 5% level. For 22% or any higher value, the probability will be bigger than 50%. So the lower bound is actually 22% and the upper bound is 100%. So this is the 95% confidence interval for P in this situation. The maximum likelihood gives the wrong values. Okay, so this one is 38 and so on and so on. Okay, here is another problematic area. This is United Arab Emirates, played 8 matches, lost 8 matches. So what's the probability? So basically, you see, what are we saying here in Hong Kong? In the case of Hong Kong, we are saying that, okay, they won 2 matches. It could be just luck. But how much luck? So basically, what is the P of winning? If the P of winning is, if their probability of winning is less than 22%, then this would be too much luck. So at least their probability of winning is 22%, and it can be any higher number. So that's a reasonable inference. Now, how about this UAE? Now we have to go the other direction. We look at square root of. Okay, so now it would be P raised to the 8th power. So we don't want to look at the square root, we want to look at the power. Okay, let's look at equals 0.05 raised to the 1/8 power. Okay, 68%. So the maximum possible value of winning for probability of winning for UAE would be 68%. And if the probability of true probability, maybe they just had a bad luck. This is what we are saying, and it's possible. So by bad luck, so if even if they have a probability 50% of losing, 50% of winning, it's possible that in 8 matches, by bad luck, they lose all 8 of them. But if their probability of winning is 68%, then this is too much. And so this is the upper bound, and the lower bound is 0, of course. Okay. So this is the traditional statistical inference, which works all right in large samples. In large samples, these numbers are correct. In small samples, they can be bad. Now let's look at the Bayesian inference procedures, which is something that you have studied on your own in the chapter. So I want to just review it briefly and start on this material, and then we will take it up in greater detail. Okay, so what we do is we put the prior density on pi. Okay, so first, now I've shown you how we do conventional inference on these probabilities. So I can calculate the probability of winning for each team according to conventional inference, and the probability according to conventional maximum likelihood in estimation. It will be just the observed proportions. The observed proportions are fairly good estimator in large samples, but very bad estimator in small samples. Now, the Bayesian estimation technique says that first thing we need to do is put a prior density on the pi, the unknown parameter pi. So, I think that this book that I have assigned tells you about the Bayesian point of view, so that we have some information which is being summarized by the prior, and then we have data information, and we combine the two to get posterior. So here's the prior. One of the special cases of this prior is that A equals 1 and B equals 1, which is the uniform prior. So then you have flat, all possibilities of pi are equally likely. So that's one special case. We will look at that, and we'll look at the general case also. So now the posterior is obtained by multiplying the prior with the likelihood. So you get this pi to the a plus y minus 1, 1 minus p to the b plus n minus y minus 1, where we ignore the constant. I think I already did this calculation in one of the lectures. So basically what we get as a posterior is another beta density, and the beta density has the parameter n plus a plus b and a and b. Yeah, the parameters are x plus a and n plus a plus b. Those are the two parameters of the You should have derived this sometime ago. Anyway, okay, so now there are two things. Okay, so the Bayesian estimator is okay. Let's now look at the Bayesian estimator. So I'm going to okay. So I'm going to put A and B as 1. This is 1 and this is 1. This is the A and B that I'm going to use. And now the estimator is simply x plus A divided by n plus A plus B. Right? If you remember that. So I'm going to use then the estimator, the Bayesian estimator is going to be equal to 8 plus A, which is $J $1. Oops, I want a parenthesis here. And then I want to divide this by n, which is over here, plus $J $1 plus $K $1 parentheses. Okay, so now this is not very different from So you see the Bayesian estimators are quite a bit better. Oops, I shouldn't have done that. Anyway. Okay, this is the Bayesian estimator, and now Okay, so you see here it's 47% for Afghanistan. Australia had an 83% an MLE, and it had 65% to 100%. And now the Bayesian estimator is 80%. It's less than the 83%. And similarly, Bangladesh is 70%. England is 48%. Hong Kong is 75%. Now you see it's much more reasonable than the 100% and 0% because the Bayesian estimator is shrinking. This is one very important characteristic of the Bayesian estimator that basically it's combining the prior information with the data information. A priori, before we know anything, the prior mean is A over A plus B, 1 over 1 plus 1, which is 50%. So if I don't know anything about the team, I will guess that it's 50%. Now, if I learned that the team actually won 83% of the time, which is the case for Australia, then I'm going to mix this information with the prior information. So, prior information says 50%, data information says 83%. So I'm going to choose a number which is between these two. But there is even more sophistication in the Bayesian estimator. The Bayesian estimator not only mixes them, but it also mixes them according to weights which are according to the number of observations. So actually there's the concept, I think it's discussed in your lecture notes, of equivalent observations. So the prior is equivalent to a certain number of observations, 2 or 3. So if you have 2 observations which say that the team, okay, so you basically the prior you can think of as adding extra data. So I have extra data, I have 2 matches that I saw, this is my prior, and in one of them the team won and one of them it lost. So now I have 2 matches in which I have 50%. Now I add on the additional information. So for the case of Hong Kong, I saw 2 additional matches and they were both victories. So now I have 3 victories out of 4 matches, so 75%. And so I'm shrinking, and basically I'm doing an equal weights, 50% from the prior and 100% from the observations. So my estimate is 75%, which is an equal mix of the two. But in the case of Australia, we don't have an equal mix. We have 83% from the trial, but that's because there are 18 matches. So now I have 18 matches of information which give me an 83%, and I have 2 matches of information which give me 50%. So the 50% is not very reliable because it's only based on 2 matches. So I merge these two. I say, okay, we go from 18 to 20 matches, and we have 16 wins. So then we have 16 out of 20, and that will give me my 80%, which is exactly what I have. So basically, it's a very sensible way of combining the prior. And basically, it also shows that the influence of the prior will disappear asymptotically. So that's also another important theorem. Bayesian theory and maximum likelihood theory become the same in large samples. But in small samples, they are different, and Bayesian theory is better. Now, the last thing that I want to do is look at the credible interval. And basically, the credible interval is the replacement for the confidence interval. Okay. Oh, acha, I got rid of this one. No wonder. Okay, so now the credible interval for the beta will be... okay, do I have beta density here? I don't know. Beta inverse, wow, that's great. Beta dot inverse. Now, probability. So I want the 5% probability to get the lower bound. Oh, wonderful. I thought I wouldn't be able to do this because it would take too long, but it's built in. So now what is the alpha? In the posterior, it's no x plus 1. So x is the huh? Yeah, 1. The number of victories is 1 is 8. So 8 plus 1 is 9 is going to be the alpha. And what is the beta?
B plus y minus
B plus n minus y.
B plus n minus x, right. So n was 8 plus 9 is?
So it
B plus n minus 1.
y is 8.
Okay, wait. Let me. I'm going to do this by. I want to have the whole column. So it's this is C2 plus 1, comma, and now it's going to be B1, right? B2. B2 is the n, right?
18.
Acha, it's also D2, the number of lost. So it's D2 plus 1, right? That's all, right? 1 plus, yeah, right. So it's D2 plus 1, that's my B. And finally, what do you want? Nothing? No. Nothing, that's it. 29%. And now I want the same thing equals beta dot inv of 0.95, comma, now I have C2 plus 1, comma, D2 plus 1, parentheses. Okay, so the 95% confidence interval, according to the Bayesian theory, is going from 29% to 65%. Compare it with the classical, which is going from 22% to 71%. Not that much different. And now we can do this for everything. Convert it to percentages. And now we can compare. Okay. So here we have, in the case of the Australia, it was 65 to 100. This is 64 to 92%, which is sharper interval, smaller, yani, and the central value is 80%. When you have basically the classical confidence intervals are always symmetric around the true value because they are based on normal distributions which are symmetric, but the Bayesian, the beta density is not symmetric, it's a little bit skewed, so you have the estimate is not right in the center of the confidence interval. So that's not a big issue, but okay, so this is 70%. What I wanted to look at was the 0. Okay, 0 has 95% confidence interval going from 37% to 98%. Remember that the confidence interval we got was from 22%, so this is higher than that, but it's a reasonable inference. So okay, so that's it. Here for United Arab Emirates, the probability of winning is between 1% and 28%. So it's not even made into 0, which is the... So basically you can see that here, for example, there's a big difference. This is for West Indies. West Indies plays 15 matches. Now the confidence interval in the classical goes from 4% to 15%. This one goes from 14% to 50%. The estimate of winning is 29, which is almost the same. Okay, so that's the first.
सर हमने दूसरे इंटरवल के लिए 1 क्यों ऐड किया, D2 plus 1 किया, जैसे हमने अल्फा के लिए किया था, लूज को तो जब हम फार्मूला में पुट करेंगे तो वो नंबर ऑफ लॉसेस जो है वही हमारे इक्वल आना चाहिए, उसमें 1 ऐड कर दिया n माइनस y प्लस 1 है ना, तो y प्लस 1 नंबर ऑफ विनिंग वो जितने भी इस केस में, तो n माइनस y कर देंगे, विन माइनस करेंगे तो लूज नंबर ऑफ लॉसेस ही आएंगे, तो यहाँ से सिंपल d आएगा, d प्लस 1
उसके साथ एक प्लस
There is a 1.
n माइनस y प्लस 1 ना.
Okay, check it. Yani, maybe I made a mistake. You should be able to fix it. But basically, the goal of this lesson is very important, that I am doing a comparison between the classical inference and the classical point estimator and the classical confidence interval. This is the end result of classical inference. Unfortunately, you see, the classical textbook, it teaches so many things that you don't understand what you are trying to tell. And this is the only thing. This is the end result, the final, after every calculation. This is the estimate and this is the confidence interval. That's it. This is what the whole goal of classical inference is. And now I have compared it with the whole goal of the Bayesian inference. And we can see that they are giving more or less similar results. And they give, as I showed you, because if you think of the prior as a additional data point, so it's giving you 2 additional data points. So if you have 100 points, then those 2 points, whatever they are, it won't make any difference, more than 2%. So the classical inference and the Bayesian inference will be exactly the same. If you make your prior very strong, and you can, the Bayesian allows you, instead of 2 data points equivalent, you can make it 50 points, then it can have more influence, and different values of A and B will give you a different amount of data equivalence prior. So basically what we like to do is, in Bayesian inference, unless we have prior information, you should keep fairly what is called an uninformative prior. It should have fairly low value, but even that low amount fixes some serious problems with classical inference in small samples. Like if you get only 2 wins out of 2, then the classical inference completely breaks down, because the maximum likelihood is 100%, which is not at all reasonable. And then the confidence intervals also break down, so everything goes haywire. So the Bayesian inference works well in small samples, and the other important thing about the Bayesian is that it shrinks towards the prior mean, and it shrinks intelligently, in the sense that it takes into account the amount of prior information, and according to that it gives the weight to the prior information. And it takes into account the amount of posterior information. So if the data information is large, then the data gets a lot of weight, the prior gets very little weight. And if the data information is small, then the prior gets much heavier weight. Okay, so that's it. Now what I would like, I think that's all for today. Now the thing is for administrative issues.